All right, so this says alkene reactions. Are they substitution, elimination, or addition reactions? So how would we classify them? So we have our alkene, we have X and Y, and then we have our product. So go ahead and pause the video and choose which one of the reaction types this is. Okay, hopefully that was pretty easy. This is an addition reaction, right? We added X and Y to that molecule. So why do addition reactions happen to alkenes? So things we've talked about before, the pi bond is weak. The pi bond is weak, so that's the first kind of thing, the reason why these happen. Remember, a CC sigma bond is 368 kilojoules per mole. A CC pi bond is over 100 kilojoules weaker, 267 kilojoules. Weaker bonds are more reactive. Also in organic chemistry, negatives flow to positives. We have a negatively charged pi bond, so the pi bond is electron rich and negatively charged. Remember, what does that look like in our molecular orbitals? We have this pi bond above and below, and we can see in a electrostatic potential map that you can see that electron rich region right in between the two carbons of that pi bond. So if we have an electrophile around, if X or Y is electrophilic, that pi bond is going to give its electrons to that molecule. So that is why and how addition reactions happen in general. All right. In these addition reactions in alkenes, we are adding atoms to that pi bond, but they can add to the pi bond in a variety of ways. The ways that the terminology we use to describe the reaction can be a syn addition or an anti-addition. So what does that mean? Well, if we have our cyclohexene here, and we have the pi bond of that cyclohexene right here, syn addition means that the atoms that are added to the molecule are added to one face of the alkene. So if a syn addition occurred, the things that were added would be added to just this side, just the blue side, or just the green side. Not one thing added to the top, one thing added to the bottom. So syn addition means that the atoms are added to the same face. So atoms added to the same face. And this is a reagent that we'll learn later. It's called BH3. The reaction that we learn about it, the complete reaction will be called the hydroboration oxidation. The first step is a syn addition of BH2 to one side of this alkene and the pi bond to that hydrogen. I'm going to draw the reaction arrows in right now. It's not necessary for you to know those, but essentially the pi bond grabs that, and these electrons are broken toward the boron, and they're used to make a pi bond or a sigma bond to the other side. So if that added to the top, that would mean that we would have the BH2 on a wedge and the H on a wedge. And if it added to the back face, we would have the BH2 on a dash and the H on a dash. So the boron and the H were added to the same face, either all on the top, and if that was the case, then it would be the wedge, or all on the back, and that would be the dash. Anti-addition, this is kind of I can't show all the arrows for this mechanism in a single step like I did here, so I'm not going to put them in, but anti means that the atoms are added to opposite faces. Atoms added to opposite faces. So it turns out that when we had bromine or chlorine or iodine to a pi bond, it's going to make a mixture of anti-addition. So one anti-addition would give that molecule right there. The other anti-addition would give the molecule right here. What is the relationship between these molecules here? hopefully you were able to say that these are enantiomers. So this anti-addition did provide a mixture of enantiomers here. In this case, technically, there's no stereocenter on this molecule because even though this hydrogen was added to the same face that that boron was added to, there is also a hydrogen on the back face over here. So these are technically the same molecule, but they do demonstrate that syn addition of those two atoms and the anti-addition of those two atoms with these two different reaction schemes. That being said, some reactions like this one and this one only do syn or only do anti, but also there are reactions that can produce a mixture of syn and anti addition. How are we going to figure that out? Really trying to understand the mechanisms will allow you to figure out which one is going to add syn, which one's going to add anti. So we shouldn't be focusing on memorizing this one's syn, this one's anti. It's just too many things to memorize. We should be thinking through the mechanisms and understanding them and then relating that to this terminology. But we have to know the terminology first. So that's why I introduced it first. All right.